This looks like a good book. It's a very modest title, right? All the statistics. This is for Aaron's class?
Yeah.
Okay, we're rolling. Everybody happy? Any questions? No? Do you have a test today? The due date's there. Homework, the details are posted. Yeah, I did it like 4 minutes ago. I love to do that to you. So what do you have a test in? Ken? Oh, Ken's class. Okay. Yeah, he was whining on Facebook about having to make up that test. It's like, well, whining about taking the test is one thing, but oh, so you've already had the test. It was just before this?
Yeah. Some of the chapters in our book are shorter than the test.
All right. How many people are in that class? All right, cool. I'll complain to Ken. And I'll tell them exactly who is complaining. Yeah, well, they've been called a lot of things. Okay, so merciful, I don't know. So we're going to finish up classification and just move on to the next logical topic, which is clustering. And hopefully today I'll get through what's known as flat clustering or partitioning, and then we'll talk a little bit about hierarchical clustering. I don't know whether or not we'll get through all of this. Sorry, I'm laughing because he's got an apple stuck in his mouth in the back. Just spin the camera around and get a shot of him. He doesn't even know I'm talking about him. Okay. So just to summarize the support vector machine last time, I got a lot of questions from people about how much of this stuff do I really need to know. Really, for the purposes of this class, which is not a machine learning class, you don't have to know the details of the math behind how SVMs work. What you have to remember is basically the points here that essentially, for all practical purposes, you can think of SVMs as being a fancy kind of linear classifier. They are, at their core, binary classifiers. They make it fairly easy to represent large numbers of shallow features, and it's fairly easy to concoct new features and throw them in. Training time for SVMs can get quite expensive and prohibitive. That's why one of the points here is that there are cheaper methods. And when you're talking about advanced machine learning methods, whenever anybody says method X is cheaper than method Y, what they're really talking about is training time, because that's usually where the critical resource problems are. Although, as you remember from using K-nearest neighbors, in K-nearest neighbors, the expense in doing that is at classification time, not at training time, where training is essentially memorization. Classification using K-nearest neighbors means comparing an object to every object you know about, right? And that can get prohibitive. But in general, when you hear somebody talking about machine learning being expensive, they're talking about the training time. Make sense? Okay, naive-Bayes training is very quick. You just collect statistics. Much of the popularity of SVMs has come from the fact that a bunch of people have made them available, packages available for free. So you don't have to roll your own SVM package. Some of them are tuned, as somebody asked last time, some of them are tuned to this kind of data. So essentially discrete data where we're representing things as this word occurred in this document or not. So it's a very sparse incidence matrix or binary vector kind of thing, as opposed to other packages that are designed for the more numerical kind of things where the values that a feature take on may be a real number. Okay? So SVM Lite is one of the popular ones that people use for this kind of text stuff. So it would be perfectly appropriate in, say, a course project to go Google SVM Lite, download the package, install it. You don't have to know anything about how it works. Just boom, make it run. Okay? Yeah, that's all you need to know about SVMs for now. Now I'm going to switch and try to finish up the slides I was trying to get through last time. So this is basically practical advice on how to run these things. The important part here is basically what you discovered in the first and second homeworks, which is that out of the box, you take Lucene out of the box, you run it, you get 0.23. You spend a week and a half or a weekend or 3 hours, depending on who you are, noodling with it to stick in different analyzers boosting a few things, trying a couple of other tricks, and all of a sudden it goes from 0.23 to 0.4. And that's with a week's worth of tuning. That's, and most of you didn't really do anything that was particularly medical specific. It was just trying the usual set of bells and whistles and to see where you can get. Once you get to that 0.4, if you really want to go on with this, right, then you'd actually start doing stuff that was fairly specific to this particular collection. You try to figure out the right kind of tokenization to do so that you're breaking things up into the right kind of tokens and figure out what the right morphology is for the medical domain and all that kind of stuff. Maybe doing a better job with creating a realistic thesaurus, maybe doing some stuff with acronyms, because there's a lot of acronyms in this kind of data. And all that stuff is going to be stuff that's very specific to this particular collection. So that's what they're talking about here, is that one-size-fits-all tools don't really do the job for you. If you're going to actually get a package and pay big money for it from some vendor, what you really care about is not out-of-the-box performance. What you care about is how easy does that package make it for a developer to actually tune it to the collection that you care about. What kind of analysis tools does it give you? What kind of analytical tools does it give you? That kind of stuff. Make sense? Okay. Here what we're talking about is how much data do you have? And how much data you have actually matters the most for text classification. So you have none, very little, quite a lot, huge amount. These are fuzzy categories. Well, none is not fuzzy. None is fairly discrete. If you have none, you're in trouble. What do you do? So if you have none or very little, what you usually do have is some in-house expertise, right? So if you're building an application like for the medical stuff, you got a doctor, or you have a nurse, or you have a medical researcher. If you're doing something for the intelligence community, then you have spies at the NSA that tell you what it is that they're looking for. If you're the sports writer for the Daily Camera, then you have somebody who knows about baseball or football or whatever. So that's what it means by having domain expertise. That means somebody who knows what the domain is all about. And if you have that, then it's perfectly okay to get started. So just start writing some rules. Right? So that rule there basically says, you can read that as, does it contain this word or that word? If it contains those words, then let's put it in a particular category. It's easy to write those. Everybody loves to write regular expressions. Managers, particularly software engineering managers, love regular expressions because they understand how they work. One of the reasons that people like to use them is not only do you understand how they work, you understand how they fail. Right? So if you get a particular document that's being put into the wrong category, you can look at your rules and you can say, it got put into this category because it was checking for this word, and this word has 2 word senses, and one of them is sports related and one of them isn't, and that's why it got put into the category. So then you go ahead and you tweak your rule by putting an or and a not in it, so that if it contains this or that and not this, then that goes away. Does that make sense? On the other hand, if you're using something like an SVM, right, and your manager comes to you and says, why did this document get put into this wrong category? Because the 14th coefficient of the 3rd dimension of the hyperplane had this too close to the boundary, or the kernel that we used that projected into a higher dimensional space projected into the wrong part of the space in the hyperplane. There's nothing you can do with that. Right? So was also something that was a criticism in the old days of neural networks, because for a while there, neural networks were the popular way of, voodoo for building machine learning systems. It was the same kind of thing. It was just a bunch of floating point numbers. All right? So with careful crafting, this means that tuning to some kind of development set that's representative, you can get high performance, 94% recall, 84% precision over 600 categories. This goes back a way. This was a system that was built by a bunch of grad students at Carnegie Mellon that spun it up into a company called Construe, which eventually got bought by somebody. They're probably owned by Autonomy by now. Did that acquisition ever go through with HP?
Yeah,
it did. What they wound up paying? How much? $12 billion for a naive-Bayes text classifier. It's not true, but that acquisition that he's talking about is HP bought Autonomy. Autonomy is the principal document classification, management, routing, and analytics company out there right now. Got into pissing match with Larry Ellison and Oracle, because Oracle was going to buy it but decided it was too expensive, and then Larry Ellison started criticizing HP, which seems to be one of his favorite hobbies. And then it got into the newspapers, and these two companies are just basically... and if Ellison gets mad enough, he'll just buy HP and fire everybody. All right. So what if you have very little data? Basically, if you have some data, more than none, but not a lot, this is basically saying stick to something with high bias. What does high bias mean? Remember, variance and bias. It's good memory. Generalization, bad memory. Nick has a bad memory. So high bias means you should stick to an approach that tries to come up with some kind of generalization as best it can over the little amount of data that you have, as opposed to a method like k-nearest neighbors, which is essentially a memorization-based method. If you don't have very much data, then there's no point in memorizing the data, right? So if you're trying to distinguish dogs from cats, and I show you 2 Chihuahuas and a Siamese cat, and you memorize them, and then I show you a German Shepherd, what are you going to do? Right? There's nothing you can do there, because chances are if you have a small amount of data, you've got not enough to hope that those particular examples are going to match exactly the examples that come in. High bias means come up with whatever generalization you can possibly come up with from that small amount of data. Now, the example I gave you is kind of bad, right? Because you're going to come up with 4 legs. Well, cats have 4 legs. Does that make sense? Stick to things that are not memory based. Now here we haven't talked about this, and this is actually a big bugaboo in information retrieval and in machine learning and natural language processing these days. The difference between these 2 bullets. So what the first bullet is saying is that an interesting research approach is to explore semi-supervised training methods, bootstrapping, EM over unlabeled documents, blah, blah, blah. Essentially what that's saying is that, well, you could try something like the following. If you've got not none, but some, you've got some data, train one of these high bias methods, like naive Bayes, on whatever data you've got. And now you've got a classifier. And presumably in the background, you've got lots of other data. So when I say how much data do you have, what I really mean is how much labeled data you have. How much data do you have where this document has been labeled with the exact category, and this document's been labeled with this exact category. Most of these domains, having just unlabeled documents is easy to get. So if you can get some, then you use naive Bayes to train a classifier. You've got lots of unlabeled data. Heck, take that unlabeled data and run it through your naive Bayes classifier. Now you have lots of labeled data. So what do you do with that lots of labeled data? Retrain. And in a perfect world, you retrain using a method that requires more data, so you throw an SVM at it, instead of just regurgitating it through naive Bayes. And that usually comes under the label of bootstrapping. There's lots of different ways of doing it. You'll also hear things like co-training, active learning, semi-supervised learning, but they're all predicated on the notion that you have a small amount of training data, and you can spin that up into a large amount of training data by training an intermediate classifier. Now, it's voodoo, right? Because if it worked, then that would mean that the intermediate classifier was high accuracy. And if the intermediate classifier was high accuracy, then you don't need the more training data. You don't need the better classifier. Clearly, what we mean by not having enough training data is that the training data you have is not good enough to build a high accuracy classifier, which means that if you throw naive Bayes at a small amount of things, you're going to have a classifier that has a high error rate. If it has a high error rate, then throwing it at a bunch of unlabeled data is just going to get you noise. And then you're training on noise to get a more accurate classifier, right? So there's an art and a science to making it work right, and that has to do with being able to distinguish in that intermediate classification step which of the examples that it's labeling are likely to be right, and which of the labels that it's labeling are likely to be wrong, by using some kind of confidence measure or the naive Bayes probabilities. So if the naive Bayes probability is coming back and saying, I'm 90% sure that it's 90-10 sports medicine, then sure, I'll believe that one. But if it's 55-45, the argmax in naive Bayes is still going to give you an answer, but maybe you shouldn't believe that answer. That's a lot of hand waving in there. And the reason that's called research is because typically the only place that it's used is in a place where we already have large amounts of labeled data. And we're imagining that, well, what if we didn't have to have gone to the work of creating that data? So we'll take a small subset of it, and we'll do these experiments within this domain, knowing that we already have the real data behind us, so I can do a full-blown evaluation. Does that make sense? Okay. As opposed to what you do in the real world is, if you don't have enough data, get more data. Right? It's not there. That does not require a PhD. Right? So if you're distinguishing business articles from sports articles, and you've gone to the Daily Camera and they've given you 100 of each, and that's not enough, then you go down to the Pearl Street Mall, you pick a bunch of people, you pay them $15 an hour, and you give them a couple of thousand articles, and you have them label it. Right? I mean, that's quick and dirty and fast. Right? And an even faster way of doing it these days is to do what online? Go to Mechanical Turk. So Mechanical Turk is basically this online Amazon-mediated sweatshop where you can violate labor laws around the world instantaneously by paying people 10 cents an hour with no health benefits to get them to do piecework for you. And that's essentially what Amazon Turk is. Now, Mechanical Turk, we may talk about this a little bit later on, but it's a quick and dirty way of setting up an experiment, paying very small amounts of money, and getting judgments that are labeling judgments on things. The rule of thumb with Mechanical Turk is that you need at least 4 agreements on the same test item and you have to do filtering on IP addresses. Basically, you want people who are actually native speakers of the language that you're looking at, and not just claiming to be native speakers of the language that you're looking at. And there's lots of little tricks that you have to do to make it work right. But if you do all those tricks, you can get high accuracy labeling on relatively simple tasks. So getting more data is the right answer. There's one right answer. Okay. If you have a reasonable amount of data, use an SVM. If you're using a supervised blah, 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 you probably, this is basically the point I was making before. Even with an SVM, even with a reasonable amount of data, you're going to have pathological cases where the same kind of documents keep getting misclassified in the same way. Either they're usually winding up in that confusion matrix. If I've got 50 categories, then I have a 50 by 50 confusion matrix. Some of the documents are just the wrong type or showing up in the wrong cell. You can retrain all you want. You can get more training data, but it's always easier just to stick in a Python script at the end that says, if the document looks like this and it's saying X, put it in Y. Right? This is like the true-false question I talked about. The kid a couple of years ago who got every true-false question wrong in one of my exams, the set of quizzes. On the final, I told him, just say the opposite. Whatever you think the answer is, say the opposite. So just don't try to learn the material. If you think it's true, say false. And he did that. He did fine. So that's what this is like. I mean, that's what I mean by a hack with regular expressions. Okay? All right. Now, this is actually kind of funny. If you've got a huge amount of data, if you don't sample it correctly and you just try to train an SVM on, say, millions of training samples, then it'll take you 3 weeks to train. It may not converge at all, depending on how many features you've got and how you've got things set up. So you may want to downsample the huge amount of training data. But the alternative to do is to not use the SVM at all. If you've got a huge amount of data, just use naive Bayes. This sounds a little bit quirky, but usually what happens, this is where I was going to, the book has a plot on this, which I thought I had, but learning curves, I draw on the board, will it show up? Okay. So learning curves in machine learning systems tend to look like this, where on the x-axis, what we've got is amount of training data, and on the y-axis is some kind of performance metric. So with a small amount of training data, adding a little bit more and a little bit more, your performance tends to zoom up. And then at a certain point, your performance tends to just asymptote. It may not asymptote completely, but its rate of improvement drastically reduces. Make sense? And typically, on a lot of these machine learning data sets, when you have a large amount of data, it gets to the point where in order to get something like a 1% improvement in performance, you've got to double your training data. So if you're way out here on the curve, you know, from a purely economic point of view, you have to ask yourself, do I want to go from 1 million items to 2 million items in order to go from 85% accuracy to 86% accuracy? Especially if the customer is demanding 90% accuracy, that's going to require 10 times as much training data. Right? That asymptote there starts to kill you. Does that make sense? All right. So the other thing that happens with this curve is that you might have really smart approach X. It looks like this, and so this is X and this is Y. I should give them different names. So this is SVM and this is naive Bayes, where a smart system on any given fixed amount of training data is going to outperform a dumb system. Right? So SVMs are going to outperform naive Bayes. That make sense? Except when you get out here. The marginal difference between the two approaches diminishes as you get more and more training data. So if you're someplace like this, and you want to make up this difference, and you've been using naive Bayes, do you advertise to hire somebody who's got a PhD in machine learning from Carnegie Mellon and pay them $200,000 a year in order to get your performance from here to here? Or do you go down to the Pearl Street Mall and do that amount of additional labeling to get naive Bayes to go from there to there, which is the same as that is? That make sense? Right, so the dumb approaches equal the smart approaches if they just have a little bit more data. So why bother? Okay. Sort of a why bother slide. Okay. It's also easier to debug them. Another thing that you're facing on the current homework that I know you've all started working on. How many people started working on the homework? Jessica. 5 points for Jessica. The examples in the book and the examples of the SVMs are always, is it sports or is it medicine? Is it spam? Is it not spam? Is it pornographic? Is it not pornographic? These sort of binary classifier kind of things. But most real-world domains aren't like that. So with the mesh terms that I gave you, I think I said there's 4,900. I think if you actually look at the medical, the mesh, the NLM page for the mesh thing, I think they're up to 10,000 terms now in the actual official vocabulary. Yeah, that makes things much harder, right? It makes evaluation much harder because some of these categories are not even differentiable. Yeah, so evaluation gets difficult. Everything gets tricky. Let me give you another example. So people know what an ICD-9 code is. Chris is not here. How many people have been to the doctor? How many people have insurance? So it turns out almost the number one thing that doctors care about these days is what? Yeah, yes, getting paid, right? So in the U.S. insurance-based health system, if you go to the doctor and you have a heart transplant or you have bronchitis, it doesn't really matter. There's something called an ICD-9 code, code, that basically is a code for that particular treatment. Right, so when you're at the doctor's office, that's the code that they pick. You know, patient came because they had bronchitis, and that's some particular code. That's what goes into the billing system. The billing system goes to the insurance company. That's how they get paid. You know, if it turns out to be the case that they're doing Medicare and they put the wrong code in and it goes to Medicare, they get sued. Right, they get taken to court because if you, I meant bronchitis, but I said heart transplant, right? And the reimbursement is, $10 versus $10,000. That's called fraud, right? So it turns out that there's all these companies out there that do ICD-9 coding. So an ICD-9 coding is a human task where people look at the billing statements, they look at the record, and they actually say, this is the right code, and this is how you're going to get paid. Right? And I think that there's currently 16,000. Did anybody see the Wall Street Journal article about this a couple of weeks ago? So I'll dig it out and send it to you. It's hysterical. So they're going from ICD-9 to ICD-10. The current system has 10,000 codes. So if you're an ICD-9 coder, in your head you have medical knowledge that allows you to classify the text from a patient record into one of these 10,000 categories. ICD-10 has 100,000 codes. And they have codes that are really insane. Like, bitten by a raccoon is a code. Bitten raccoon for the second time is an additional code. Right? And it's not just raccoons. They have this big list of animals that bite. Cut by glass, cut by earthenware, cut by wine glass kind of stuff. So, that's 100,000 dimensional classification task. So there's a certain amount of automation to it, but it's mainly a human processing task. Right?
So they get paid like $20 an hour.
They do. They're relatively well paid. What? They have an iPhone app for it that turns out that it's made by 3M. So it turns out 3M has the company 3M has a health division, and they own 85% of the market for insurance coding. Believe it or not. Okay. How do you tweak things? Well, you do all the stupid things that you were trying to, not stupid, all the intelligent things that you were trying to do on the homeworks. Lots of domain-specific things. Like, it turns out that if you're dealing with newspaper text, one of the things that people always throw away for newspaper text, New York Times, Wall Street Journal, whatever, is the author. Well, it turns out that there's only a fixed number of authors at most newspapers these days, journalists. For instance, fixed and dwindling. But if you read the Daily Camera, I think they have 3 writers. There's the sports person, there's the person who slams CU, and the person who talks about traffic accidents or whatever. It turns out to be an incredibly useful feature. So ignore the text of the article and look at the author, and you can classify it as sports because the sports guy writes the sports articles. Right? It's not rocket science. Same thing for spam filtering. Spam filtering these days actually is based much more on the route that the email took to get to you than it is on the actual content of the message. That's more revealing. Titles, zones in text. We haven't talked too much about zones, but and that's hard to do with some of your homeworks because they're just paragraphs. But for your projects, zones just basically means, should I look at the first paragraph? Is this in the middle of the text? Is it at the end of the text? It turns out that depending on the genre, stuff that's at the beginning, middle, or end has different information in it. So newspaper articles are written in such a way with this inverted triangle business where pretty much you can ignore the information paragraph by paragraph at the end of a newspaper article because they're written in such a way that they can be backed off from the end because the author writes the article for the newspaper and then the copy editor has this amount of space to fit it in. This is newspaper type stuff as opposed to online stuff where what are you going to cut? Cut a paragraph off the bottom. You still want it to be coherent. That means the paragraph in the front has all the information. Make sense? Lots of tricks like that. And then some of the stuff we talked about with respect to normalization and whatnot. Depending on your domain, you might want to do all sorts of kind of tricks to do processing on gene names, part numbers, and whatnot. There's a company, stop that. There's a company here in town called Silver. They're not here in town anymore. They got bought by Oracle. So they're out at the Oracle empire. Does anybody work for Oracle? Sun, Storage Tech? I used to work for Sun, so you quit, right?
No, I wasn't interested in thinking about that.
So there was an NLP company called Silver Creek Systems, and they tout themselves as natural language processing. They got bought by Oracle. All they do is deal with part numbers. So it turns out that part numbers and acronyms and abbreviations are a huge problem for big companies. So you're a company that makes ball bearings, right? You have part numbers for the 15 million different kinds of ball bearings you make. And if there are typos in there, then you ship 10,000 units of the wrong thing. So they've got a gigantic Perl script that does domain-specific manufacturing, acronym, part number, SKU analysis. It's a weird kind of morphology. Right. There's lots of things you can do here. All right. Do hacks help? Yes, this is what we just talked about. Title words, first sentences, sentences that contain the title words, all the kind of stuff that you were trying to do with boosting, you have to do sort of at a more fine-grained micro level. Again, we're really deep into the, you shouldn't try this until you've tried a million other things. And you're just trying to get from 88 to 90% performance. If you're just trying to get to some decent level of performance, you don't worry about this stuff until the very end. All right. I'm gonna speed up because the rest of the stuff is sort of in the book. Concept drift is worth talking about. It's basic, and it leads into the next topic that we're going to talk about. Where do these categories come from? Well, you know, the high-level categories like sports and medicine, they're not going to go away. But the more fine-grained categories are based on things that have a temporal dimension to them, like who's the president of the United States. If you assume that your data is static, then you can do all this developmental overfitting all you want. But if you do that kind of overfitting and then just plant it out in a system that's online and working and pretend that you're going to forget about it, then, you know, every 4 years everything's going to be classified wrong. If you're talking about the president, and if you're talking about who won the World Series, and if you're talking about the Super Bowl, lots of things sort of come and go. So this notion of a concept drift is that your system's going to learn something that's, you know, ephemeral. You know, it's not the hottest thing going on right now, which means that even if you're doing machine learning, you need to have people around to keep the system tuned and up to date. Okay. So like some of the stuff that we're doing in that Twitter being used in crisis situation stuff, that's, you know, monitoring social media for how people use Twitter in crisis situations. There's always the crisis of the month, right? So you can look for a keyword like earthquake, and if you look for a keyword like earthquake last month, it was the earthquake in Virginia, right? That happened just outside Washington, D.C. and hit the East Coast. The same keyword for the next earthquake is not going to be about the same event. Right? So there's sort of a notion of a topic that's sort of temporally coherent that becomes different over time. All right. Blah, blah, blah. Okay. I'm going to talk a little bit about clustering. So switching gears. Classification, somebody came to you and said, these are the categories. And not only that, they came to you and said, here are a bunch of the documents that belong in category A, and here's a bunch of the documents that belong in category B. Here are the documents that belong in category C. Not only that, in all the stuff that I was just talking about, I was making a hard partitioning assumption that this document belongs in this category exclusively. So documents belong in particular categories, and the categories span all the documents. So there's no other category, and this document cannot belong in two categories. Right? Those are pretty ridiculous assumptions, but that's what's underlying almost everything we did. All right. So where do they come from? Right. So usually it's because there's somebody who's trying to make money by making some distinction, and that distinction is well understood ahead of time, but that's not always the case. And clustering comes in the situation where maybe you don't know what the categories are. So can a system automatically discover the categories and potentially discover the categories in a collection, freeze them, put them on the shelf, and then turn the problem into a classification problem? So learn the categories and then learn to do categorization. Or you may want to make the assumption that, no, there are no fixed categories. It's always a matter of doing online, on-the-fly clustering. Okay? So clustering is the predominant form of what's called unsupervised learning, as opposed to the stuff we were just talking about, which is supervised learning. It's not the only kind of unsupervised learning, but it's the easiest example to explain. Okay, and that's what we're going to focus on. All right, so within IR, there's a number of different ways of talking about why you want to do clustering and where you might want to do it. There's a sort of overarching paradigm, which doesn't really get you very much, but is, do I want to take my entire collection of documents, say your medical texts, and cluster that ahead of time, and then use that somehow to improve search? That's usually referred to as the cluster hypothesis. So the cluster hypothesis is, if we can do that the right way, then doing unsupervised clustering on your 50,000 medical documents can somehow make your life better in processing those 63 queries that I threw at you. Right? That's sort of a still hypothesis. It's one of those things where scientifically somebody came up with a hypothesis. It's been proven wrong for the last 35 years. And so in this domain, nothing ever gets proved wrong. It's just waiting for somebody to make it work. Right? So PhD thesis after PhD thesis doesn't seem to help. The other place that clustering, that's clustering the entire collection. The other more useful place that clustering comes in is clustering the results from a return set. So you have a query, you've submitted the query to your retrieval system, you're getting your top 50, your top 100, your top 2 million, whatever it is, and then you run a clustering algorithm on that. So that's a dynamic set. It's not the entire collection, it's just the set of documents that have been returned given the query that the user asked. Okay, so why might you want to do that? That's to make the user's life better. If you can take that screen of initial results and divide them up into the different categories that are actually there, then the user can zero in on the thing that they actually want to zero in on without having to wade through all these irrelevant results. All right, so let me, not that one. Okay. So there's a search engine out there called Yippee. I have no idea what its market share is. It used to be called Clusty, and I have no idea what its market share was, but it did get sold. So hey, even if you have like a 0.1% market share in search engines, you can do ads and you can make a decent living. So you don't need to be Google in order to make a lot of money. So Yippee has a lot of, I can't believe I say this. Yippee has a lot of things in it. So I'm just showing you one example. So let me show you the Google version of this first. So I queried on pirates. It's just a single word, pirates, and I've got 275 million results. And even if so, the top one is an ad. In case you didn't notice that, we'll talk about this when we get to web search. That top one's an ad. You know how you know it's an ad? Because it says ad. It's not exactly the biggest font in the world. You can't really tell from on the screen, but it's a different color. It has a slightly different beige outline around it. It's also on the top of the screen. This is the most important piece of real estate in terms of making money in the search business, right? The real estate that's at the top and left. So Google's done all this eye tracking research, and it's really fascinating looking at the results of the eye tracking research, but that's the place people look on the screen. So that's where you put your moneymaker, right? So that's an ad for Pirates of the Caribbean. Right? It's relevant, but it's an ad. So the search results start with the Pittsburgh Pirates. Then we have a Wikipedia article about piracy. Again, the fact that it's Wikipedia is hardwired into Google's rank algorithm right now. They just boost Wikipedia almost arbitrarily. Okay, so we've got baseball, we've got piracy, and we've got piratesinfo.com. I actually clicked on this. This is a place that actually sells crap related to pirates. Swords and hats and bandanas and posters, and also it's not really about history and the history of pirates. Then you've got news about pirates, and this is basically modern-day pirates, which are not what people think about when they think about pirates, but maybe it is if you're following news in Somalia and whatnot. Then it's Pirates, which is a video, and then another Pirates movie, and then more about pirates. So what's going on here? It's all mixed up together. So if you go to Yippee, you get a definition of the word, which is probably straight from WordNet. That's the stuff that's up there. these results are very similar. They're a little bit different, but underlying Yippee and underlying the previous version, Clusty, this was a meta search engine. So a meta search engine is a fancy name for somebody who wrote a search engine by writing a script that takes a query and feeds it to a bona fide search engine. So you take your query, you send it to Google, or you send it to Bing, or you send it to Yahoo. You take the results from those three and you aggregate them together and you call it yours. Now that works until the big search engines notice that you're there and they shut you down. Or you make some kind of agreement with them. And you can make agreements with them. They're perfectly happy with doing this kind of thing as long as you pay them some money. All right, so underlying it, it's a meta search engine. And what they're displaying here is not terribly interesting. This is the interesting part about Yippee, is that it does clustering. So it does clustering on the search results. So it's determined dynamically that within the top 235, and there's some reason why it's not 200 million. They're doing this sampling business. They've determined that these are the top set of categories. So if you click on the plus here, it opens up a hierarchical sub-clustering of that category, that you've got hostages, you've got hijacked ships, you've Danish children, kill the pirates, fisherman attack, pirate fighting tactics, other topics. There's a bunch of stuff related to clustering that we're going to come back and talk to about, like, you know, how do they name these things and what do they mean? But that's another story. Right? So presumably we can make the assumption that everything under there is about Somalia and modern day pirates. Everything under Pirates of the Caribbean is probably about wearing an eye patch, you know, wallpaper and pictures, Curse of the Black Balls, basically the names of the movie and stuff related to the movie. And then if we get down to Pittsburgh Pirates, we'll get stuff about Major League Baseball and probably about the playoffs and other kind of stuff. Make sense? And I think it's the case that even if I go deeper in here, it's displaying, when you get down to the bottom, it's going to display basically the articles in the original return set that were from that category. All right, so this is dynamic clustering of a return set producing categories that are not pre-existing categories. They're categories that only exist by virtue of the fact that it ran a clustering algorithm on the return set that resulted from an initial query. Make sense? Okay. So the point about this is that you've got to be able to make this run fast. You've got to be able to do some level of hierarchical clustering, and you have to have some capability of naming it, because if you weren't able to name it at the top level, then the people aren't going to be able to see what it is that it's about. This is a pretty good name. Pictures is not a terribly good name, right? Because it's pictures of pirates. So is it pictures of Johnny Depp? Is it pictures of baseball players? Is it pictures of people in Somalia? I mean, what's it a picture of? Right, so that's not a good category. But the other categories are fairly coherent. Very good? Okay. All right. So I already said a little bit about the cluster hypothesis. So that's basically the notion of clustering an entire collection. And the hypothesis is that documents with similar text are related with respect to the information needs satisfied by those documents, independent of any particular query. So to improve search, what we do is going to cluster the documents in the corpus A priori, and then when a query matches the document D, also return other documents in the cluster containing D. So basically, for your point of view, what that means is take the medical documents, your 50,000, cluster them into, say, 51,000 document clusters. You know, the numbers are made up. You take the query, and then the first thing you typically do in this particular approach is run the query against some representation of those clusters. It could be run the query against the centroid of those clusters, or it could be run the query against representative documents that are most representative of each of those clusters. Pick the cluster that's the closest, and then only do ad hoc retrieval from that one cluster. That's the basic idea. Okay. Yippee is what I just showed you. So this notion of improving things by improving what's shown to the user is actually the more popular thing these days. And there's a number of reasons for that. Reason number one is that the cluster hypothesis, nobody seems to be able to make it work right. So it hurts precision and it hurts recall. So why do it? The other thing is that what users have most difficulty with is wading through the results. Users don't seem to have a whole lot of difficulty, they don't want to look at 2 million results. They want to understand what they're seeing in front of them. Does that make sense? Okay. All right. So lots of issues that we're going to talk about. Just like we talked about with classification, how do you represent the objects? Do you use a vector space model? Do you use a language model? Do you use some kind of stochastic thing? Implicit in clustering, as we'll see, is this notion of similarity. Just like we had with ad hoc retrieval, the notion of how similar is this document to this document is critical. Do you use cosine? Cosine works fine for lots of things. It's not the only one. So Euclidean distance turns out to be one that sort of comes back for clustering for some reason. So remember, Euclidean distance is how far away are these in the space. The cosine is basically how close are these in terms of where they sit in the space. How many clusters? There are a lot of clustering algorithms where you, as the user of the clustering algorithm, have to say, I want 7 clusters. Much more preferable be one that says, here's a bunch of data, and it tells you there's 7 clusters. It turns out there's lots of different ones that sort of trade those two things off. Typically, the clustering algorithms that don't require you to tell you how many clusters there are have a parameter attached to them that's a threshold, and you have to set that parameter. Setting that parameter looks an awful lot like saying, I want 7 clusters. So there's no free lunch, and so I'll show you some examples of that in a minute. Related to this stuff is the notion of evaluation. So what makes a good clustering? I mean, intuitively, the criteria that's always used for clustering is that you want to maximize the within cluster similarity. So you want the stuff that's in the same cluster to be maximally similar to one another. And counterbalancing that is you want to minimize between cluster similarity, or you want to maximize between cluster dissimilarity. So you want the stuff that's inside a cluster looking maximally like one another, and you want the clusters themselves to be maximally dissimilar to one another. And if you think about that from sort of a use case kind of point of view, it makes sense. If you've got a new object coming in, and you're going to be asked to put it into a category, your probability of putting it into the correct category, is maximized if the categories themselves are maximally dissimilar. If the categories themselves are fairly similar to one another, then you're going to have to make a choice between these two relatively similar categories. It's going to be hard to do. All right? Now, if you think about that, it poses certain trade-offs, right? So you could have a clustering algorithm that I give you 1 million objects, and it comes back and says, here's 1 million clusters. And if I give you 1 million objects, and it takes each object and puts it into its own cluster, it has maximized within cluster similarity, right? The similarity of every object to every other object in its own cluster is 1, right? So that's a win. But it's minimized between cluster similarity because everybody's in their own clusters. Some of them are going to be similar to one another, and by virtue of being put into separate clusters, I've got clusters that are similar but that shouldn't be similar. At the other end of the spectrum, you can come back and say, oh, I got 1 cluster, it's got 1 million things in it. I am maximally dissimilar to all the other clusters because there aren't any other clusters. Right? Now, I'm sort of saying that from a funny point of view, but what happens, you can sort of personify these kind of things, but with naive clustering algorithms, without having the right set of bells and whistles attached to them, you fire them up and run them, and what they come back with is these idiot, degenerate answers. And we're going to talk in a couple of weeks about EM. It's an algorithm called expectation maximization. And EM has a tendency to run to idiot answers because the criteria tells it that that's what it should do. If I want to maximally discriminate things, everybody goes in their own bucket. It doesn't matter to me if that's too many buckets. Right? Lots of different kinds of algorithms. There are more clustering algorithms out there than there are sticks to shake. And they're a very popular thing for people who are trying to propose PhD theses in machine learning. And it's usually a bad idea, but that's so the entire next 2 lectures are bad ideas. I shouldn't say this kind of stuff on camera, right? So we're usually going to start with some kind of random partitioning, and then we're going to iterate on that. And iterating on that means that if there's some partition, I need to create a new partition from the old partition. That means merging things or splitting things. And I need to have some kind of criteria that tells me how good the partition is that I'm looking at right now, so that I know that if I merge or split, that I've made things better or worse. Right? Exactly the same thing we talked about when we were doing the linear regression stuff. I've got something, I've got some number attached to how well it's doing right now. If I move it a little bit, did it get better or worse? Okay. We're going to talk today about k-means and then a little bit on hierarchical agglomerative clustering. K-means is good because it's easy to illustrate, and it works astoundingly well, even though it shouldn't. It's sort of the k-means is sort of the naive Bayes of clustering. Even though it's not probabilistic, it takes no time at all to implement, and it works shockingly well. Okay? So just to talk a little bit more about what we're going to do for k-means and for partitioning, a partition is, I got a million things, everybody's got to go someplace. So there's going to be a certain set k partitions. Everybody's only in one place, and everybody's in a place. Right, so all the objects are accounted for, and they're accounted for by being in one partition. Right, so there's no business that I'm a little bit here and I'm a little bit there. Right? And we want to find that partition that maximizes some partitioning criterion that basically is balancing off the within similarity against the between similarity. If I've got n objects, how many partitions are there? How many possible partitions are there? Very good.
And options we want to choose them into k places?
Yep. And choose k.
No, it's not quite right.
It's not.
So it's actually n plus k minus 1, choose k minus 1.
And which roughly is going to turn into what kind of number? Big. Roughly a number that's related to factorial in the size of n. Right? So all that means is that if I'm giving you something like 1 million objects to find partitions for, then roughly you're going to be looking at 1 million factorial possible partitionings of 1 million objects. Is that a big number? Right. So this is just a long-winded way of saying that you can come up with some kind of criteria that tells you how good a partition is, but you're not going to have an algorithm, not in this lifetime, that is going to search through all possible partitionings and then assign a goodness criteria to each of the partitionings and then return back to you the partitioning that's the best possible partitioning, because there's too many partitions. Right? So that's not the kind of algorithm we're going to do. Almost all these algorithms have some kind of really stupid, greedy structure to them that is going to say, here's something, let's see if we can fix it, and move on from there, but we're not searching through the space of all possible clusters. All right. Okay, so let's look at k-means. So in document world, you can think about this as back to the vector space model. The documents are vectors. And clusters are going to be, the basic part of the algorithms is going to work on centroids. So a cluster is going to be a set of documents. A centroid is nothing more than the vector that represents the average vector of those documents. Right? So you've got a bunch of vectors in a cluster. You add them up, divide by the number of clusters. Divide by the number of vectors. That's your centroid. Does that make sense? Okay. So that's just adding them up and dividing. That's the centroid. So basically, we're going to do an iterative reassignment of instances to clusters based on the distance to the other current cluster centroids. Now, on the quiz that's coming up sometime in November and in the lecture later today, it's important to keep track of distance and similarity, because the way these things are always described is with stupid examples in 2D, where greater distance means less similarity. right? More similar means less distance. So more means less, and less means more. Okay? Just keep that in mind. All right, so this is k-means. Now, this is almost literally the entire algorithm, so this is why k-means is popular. So what I'm going to do is, the user tells me, given the set of objects that I've got, I want k clusters. So k is given. The number of clusters is given. So first thing I'm going to do is, from my set of documents, I'm going to randomly select k documents. So I want k clusters. I'm going to randomly select k documents. And I'm going to call those initial set of k documents the seed documents for a set of k clusters. And those are basically going to be used as the initial centroids. All right, so those are our anchors in space. So then after I've selected the k clusters, I'm going to loop through all the documents in the collection, and I'm going to compare each document in the collection to each of the k centroids, or in the first step, to each of the k seed documents. And so for each document, I'm going to say, who are you closest to? Right, so basically, I'm going to compute the distance between each document in the collection and each of the centroids for the k clusters. I'm going to say, who are you closest to? Whoever you're closest to, that's the cluster you're going to get assigned to. That should be assign di to the cluster C sub j such that so cluster sub j is represented by the seeds, S sub j, and this should be a di, right? Not an x. Okay? Does that make sense to everybody? Right. Once I've done that, now I have a set of clusters because I've assigned every document in the collection to some cluster. So since I have documents, all the documents in the collection are assigned to some cluster, I can compute the centroid of all those clusters. So now I'm going to reassign the S sub j's to be the centroid of the clusters. And I'm going to go back up and do this again until some magical stopping criterion or convergence criteria is reached. John, make sense?
Briefly, the last line is recalculating.
So this initially is going to be explicitly the seed documents that you selected. They represent the centroids of the initial set of clusters, which don't have anything in them. Then each of those seeds is going to have documents basically paired up with it. Having paired them up with it, I compute for each one its centroid by adding up the documents, adding up the vectors, and dividing by the number of ones that are in that cluster.
Do you recompute the centroid every time you assign a document, or do you assign all the documents?
You assign all the documents, and then you recompute. All right, so this is sort of a batch update kind of thing. All right. So we do the magical 2D example would make it all clear. Nick.
How is that reducing the size of the cluster?
It doesn't. No, it doesn't reduce in this. So the cluster size is fixed. It's k, but it's going to turn out to be an iterative, greedy algorithm, and you'll see we're not searching through anywhere near a particularly large search space. So this is not k factorial partitionings we're looking at. So clearly, when you're presented with these 2D examples, where are the clusters? Sort of, there's one over here and there's one over there, right? Okay, so the first step is we're going to randomly select two seeds. So we randomly pick what look like a dumb pair of seeds. We've got a red seed and a blue seed. Right? And now those represent the two clusters. So we're doing k equals 2 as the example. What we're going to do is we're going to march through all the black ones, the unlabeled documents. I'm going to say, who are you closest to? And whoever you're closest to, that's going to be the new cluster. Right? So if we do that, it looks like this. Okay. So we've got a blue cluster and a red cluster. This does not look at all terribly close to the answer we wanted. Make sense? Okay. But now that we've done the assignment, we're going to recompute where the cluster centroids are. So now the red cluster centroid is the x, the red x, and the blue centroid cluster is the blue x. Those are our new centroids. Now, so we've gone through a full iteration in the algorithm. Now we're going to go back to the loop that says loop over all the documents. We're going to do a reassignment. If we do a reassignment, right? So the step between here and here basically says, now reassign not to the original seed, but reassign to the centroid that's derived from the original seed. All right. Now we have a new centroid. We're going to do it again. The centroid moves again. We compute the centroids again. We reassign the clusters again, and we come to convergence. Now, what's the convergence criteria? The convergence criteria on all these sort of pseudo optimization kind of techniques is twofold. You could look at has the centroid stopped moving? And that's not terribly bad. But an easier criteria to use is, has anybody been reassigned? Has anybody changed the category that they belong to? And if we get to the point where nobody's changed the category we belong to, we're happy. We could also do things like, well, have a very small number of documents changed who they belong to, because with these things you can get into sort of an isolation kind of thing where you're doing a reassignment of one, that moves it over, and somebody gets reassigned. And if you wait for a total stability where nothing's changing, you might wait a long time, where, in fact, nothing terribly important is changing. Make sense? Okay. Now, obviously, there's lots of bells and whistles underneath this that you might want to worry about. Do you really want? Is it really the case that you're so ignorant of the content of the collection that what you ought to do is pick 2 random documents? You must know something about the collection, right? I mean, it's hard to imagine that you don't know anything about it at all, especially if you have things already represented as vectors. The time to convergence is going to be based, at least partially, on the initial set of seeds. The other thing is, how do you know that this is the right one? Because what if it turns out to be the case that it's not quite as clean as this? So if it's relatively cheap to do this, and it's based on an initial random set of seeds, you run it, you got this, what should you do next? Run it again, right? Again, a lot of these unsupervised machine learning algorithms are not terribly, brilliant. Run it again, pick a different set of seeds. If he comes up with the same answer, then you're pretty good. If he comes up with an answer that's completely different, then run it again. Right? It's not, just keep running it until you get some kind of consensus kind of answer. Based on, you don't run it again with the same seeds, right? Right? you run it again with a different set of seeds, right? Make sense? All right. All right. So termination, you can do this for a fixed number of iterations. This is one of my favorite ones. It's like, not only does it not even look at the convergence criteria, really, it just says, do this 4 times and stop, right? And that might actually work. You can look at the partitioning changing, and you can look at the centroids not changing. Not changing means not changing very much. It turns out that if you look at that algorithm, the computation that actually is the killer computation is the computation of the similarity between a document to the centroids, because the centroids are now dense vectors. Because when I did that initial set, the similarity of the document to the seeds is a document-to-document comparison, mostly zeros, right? Back to our Lucene cosine comparison. But as soon as I have all the documents assigned to a category, and then I use the centroid as the representative of that, then I've got a dense vector, and I'm comparing each document to a set of dense vectors. That slows down the similarity comparison. So one way of speeding it up is to use a stupid word called a medoid, right? So you can imagine what a medoid is. Medoid is basically saying, don't explicitly use the centroid, pick some actual document that's somewhere in the neighborhood of where the centroid ought to be, and then use that document that's near the centroid as your object of comparison. And now we're back to comparing documents to documents, which is mostly zeros to mostly zeros. That's also used sometimes as an indicator of whether or not I've got a sort of a problematic case or a degenerate case, because you can run into situations where you've got a cluster that's been produced that sort of looks like this. I don't know what this looks like to you, but so I've got 5 documents over here and 5 documents over here, so I have 10 documents in my cluster. Where's the centroid? Right? Centroid's where my nose is, right? Right? There are no documents nearby, right? And the fact that there are no documents nearby the centroid means that my cluster is kind of broken. So I can use that where if I pick the median document and it happens not to be near the centroid, then maybe I've got something wrong going on here. in my initial selection of seeds, or in my similarity criteria, my distance criteria, whatever. Okay. Okay. So talk a little bit about evaluation. Clustering is notorious for this, right? So you can often. How many people have looked at computing surveys? The ACM journal computing surveys? Nobody. You've heard of computing surveys. Oh, there's a fly. Okay, nobody's heard of computing surveys. So computing surveys is an ACM journal that runs survey articles on particular topics. Some of the topics recur. So every 3 or 4 years, somebody writes a 30 or 40, 50-page article on topic X, and data clustering is one of them. There are, gazillions of clustering algorithms. Often in these articles, you'll see lots of stuff based on the running time. How fast do they run? They're n squared, they're n factorial, they're linear in the number of documents, they're square root of the number of documents, any number of things like that. They don't very often talk about how well they actually work. Because if you're in a real domain where you've got a bunch of objects that need to be clustered and you don't know what the correct clustering is, then how well does it work? All right, this is a typical problem in projects for classes like this or projects for independent studies, because you want to do some kind of clustering, and I say, how well did it work? And you're like, I don't know. All right. So let's talk about some of the things that people do. Anecdotal, user inspection, ground truth, quantitative measures. We always wind up using quantitative measures even if we don't know that they actually mean anything. And then utility or in vivo testing. We'll talk about what that means. Okay. So anecdotal means, I don't know, look what happened. This is not very compelling in a PhD thesis, but it shows up in a fancier form than you might hope. Right? So basically, you run the clustering algorithm, you do what I did for pirates. Did everybody like what Clusty or Yippee did for pirates? Sort of looked like it was doing some things right. Right? I don't know what you do with that. Right? Clearly, it could have done worse. Okay. There's no benchmarks, there's no comparisons. You make a tweak to the algorithm. How do you know if you made things better or worse? Right? So this kind of inspection is kind of useless. User inspection is one step away from this kind of anecdotal inspection. It means that it's not you, but you're going to get some domain experts that are going to look at it. So we're going to go out and find some pirate experts, and they're going to look at that category, and they're going to determine whether or not it's useful or not by some criteria. Again, this can be, if like in your homework, this requires you to go out and find doctors who are willing to do this. This can get expensive. Right? So sure, I'll do that. $350 an hour. Right? That's more than annotators get. Right? So ground truth comparison usually involves finding some collection where somebody else has already figured out the answers. And this is difficult. Right? All these things are problematic in some way or another. Right? So this one's problematic because if we already know the answer, why are we doing clustering? You hope it'll work on a different set, and you're hoping that the techniques that you find doing the tuning on the set that you do know the answers to are the same set of things that will work on a set that you don't know the answers to. And that's, maybe that's true, maybe it's not. So there's lots of different ways of finding ground truth, things that have already been labeled, like the homework set that you have. Right? Somebody has already provided us with the categories, the mesh categories for each of the documents. So a clustering version of your current homework would be strip out the .m fields. You don't know that at all. Take that set of 50,000 documents and reproduce the 4,904 categories that the humans who work at the National Library of Medicine assigned to all those documents. Good luck. Okay. The one thing that's used all over the place and will almost assuredly show up on the quiz is purity. So purity, sorry, I'm going to get the pens out. Will be on the quiz. So purity is basically a comparison between the dominant class in the cluster and the size of the cluster. Right, and that's the equation for it. Again, it's one of those things where it's in the book, but it's a little bit easier to see it from an example. So what's the purity in the bubble on the left? Well, there's 6 things there, right? The dominant class has 5 things, right? So knowing the answers, right? Again, to do purity, you have to know the answers. So this is a gold standard ground truth evaluation. So to evaluate the purity of this cluster, it's basically saying it's a value of 5/6, because the dominant value is red, and the total value is 6, and therefore the purity of the cluster is 5/6. In the second one, it's 6 as well, and the dominant value is 4, so the purity of that one is 4/6. And then the final one, the dominant is green, there's 5 total, so the purity is 3/5. All right, so then the purity measure for the entire thing. Take the product. Take the average. This is sort of a trick question, right? So it's not clear what to do, right? So one thing would be the average of 5/6, 4/6, and 3/5. And that's the average purity. The purity for the clustering as a whole is the average of the purity of the elements in each of the clusters. Anybody see any problem with that? If I gave you 30 seconds to right now describe to me a clustering algorithm, you would. Larger clusters are weighted the same as smaller clusters, but supposing I put a gun to your head and said, give me a clustering algorithm that's going to do good on purity. Meaning what? Every element goes into a cluster by itself, so the purity is 1. The dominant, so that red thing was in a cluster by itself. So the dominant value is 1, the total number is 1, the purity is 1. The average overall the n clusters is 1, so it's a perfect score. So if you use purity by itself, it doesn't tell you very much. If you have an algorithm that's able to choose its own number of clusters. But if you're using an algorithm where the number of clusters is fixed, right, then the issue is there skew, right? Is it trying to put the same number of items in all the clusters, or is it loading up one cluster with a lot of things and then giving a 1 in each of the other clusters? Because then we know if I'm telling you there have to be 7 clusters, and I put 1 element in each of the 6 clusters and a whole bunch of crap in the 7th cluster, the 6 clusters are all going to get a 1. And if I do a straight unweighted average, then I'm treating the almost empty clusters as being as important as the not so empty clusters.
So does knowing the answer here mean that after you already know the answer, or that once it is an answer, you can look at it and say,
Yes. Right. So here's what the issue is. So here, in the pure version of purity, where purity tends to be used in these bake-off competitions that places like Trek and NIST tend to run, they have the right answer. They know what the answer is. And when they compute purity, they compute it this way. There are other competitions that have been run where, since data is easy to get at, you don't actually know what the right answer is. Jeez. And what you can do is come in, get a result like this, and have a domain expert look at it and say, well, this one looks like it's mostly about actual pirates, and that blue one is Johnny Depp, and he doesn't belong there. Whereas in the next one over, it's really about Pirates of the Caribbean, and the green one is about some guys in Somalia, and it doesn't belong there. So you can take the output of the clustering algorithm and have domain experts induce the gold standard. And if they induce the gold standard, then you can use that to compute purity. And then regurgitate that through. Okay, I'm over time. But so what you should all have a feeling for is, I think the face that Nick was just making, was that there's a lot of math behind many clustering algorithms where the approach tends to be pretty weak, is figuring out if they're actually doing anything, which should make you worry in general. All right, so for Thursday, I want you to think more about projects, because we do have to get going on projects. And if you came in late, I have quizzes for several people, and the next homework is posted really aren't any more details than what I've already given you, but the due date is posted. So look at the assignment page for them.
And are we going to continue doing homeworks after this one, or is this kind of the final homework before the project?
I don't know.